Just like how Connor McDavid is a generational talent for hockey, Isaac Newton was a generational talent for physics, actually beyond generational. He had amazing breakthroughs in optics, light, gravity, and even invented calculus before he turned 26. This guy was phenomenal.
You read his writings, the man was connected to the universe in ways that I've never seen another human being connected.
And some of Newton's most famous work comes from his 3 laws of motion, which is what we're going to take a look at right now. Okay, so all 3 of Newton's laws of motion have to do with force. We have to know what a force is. A force is defined as a push or a pull. So think of those push or pull symbols on a door. You either have to push and apply a force to open it, or pull, apply a force to open it. So pushing and pulling on stuff. His first law, though, ironically has to deal with when there is no force. When there's no forces at all is Newton's first law. What's going to happen when there is an absence of forces? And Newton says that an object will stay at its original velocity. So to take a look at what this means, let's go somewhere where there might not be too many forces. Let's go to outer space and look at this rocket. Now in this position, it's firing its engines. That would be a force, a push on the rocket. So it's cut off those engines, and it's going to be stationary out in space, and we're not going to apply any forces. What's going to happen? It's just going to stay stopped. It's going to have an original velocity of 0, and it's going to stay at that velocity of 0. We would sum this up by saying an object at rest stays at rest. Next, let's look at if it's moving. Now I'm going to have to apply a force to get it up to speed, but then let's turn the engines off and have no forces applied. So we'll get it up to speed here. We're going to accelerate it, speed it up, and then we're going to turn off the engines, and it just stays moving. Just stays moving at its constant velocity. It was moving at the start. It stays moving if there's no forces applied. So this is summed up as an object in motion would stay in motion. But we're not out in space that often, so let's maybe look at an example here on Earth. We're going to look at the example of a car. Now we're going to have this car moving. The person is carrying a cup of coffee, and unfortunately they're going to hit a barrier. They're going to hit a curb or a large wall here. We'll say they're going slow enough that everyone's going to be okay, but we're going to have the car hit, and let's see what happens to the coffee cups. They're coming up on the barrier, and in the collision, the coffee cup continues to go forwards. How can this be explained by Newton's first law? Well, we said that originally the coffee cup was in motion, and then when the car hit, there was a force applied to the car, but no force applied to the coffee cup. So the coffee cup was in motion, it stayed in motion. It might not go out the windshield for common day-to-day examples, but even if you just slam on the brakes, you'll notice things in the car appear to go forward as they stay in motion. In this scenario, the car is going to be parked, maybe stopped at a red light or something like that, and unfortunately it's going to get in a rear end collision. So a car comes from the back, and we can see it appears that the coffee moves towards the back of the vehicle. And you may have had this if there's a quick acceleration or if something hits your car from behind. It feels like everything goes back. But this is actually an example of where an object at rest stays at rest. Let's highlight where the coffee cup was initially in this vertical plane, and then when it gets collided with, the coffee cup actually just stays in the same horizontal position. It's just the car moves forwards. There's no force applied to the coffee cup, so it stays at rest and just falls straight down. Next, on to Newton's second law, where now we do have a force. We're not talking about no forces. This is where he describes what happens with a force. We said when there was no forces, it's constant velocity. So if there is a force, it's going to be non-constant velocity, which is acceleration. So if a force applies, it has to speed up or slow down, which is called accelerate. So take this example of this person is going to push on this box. They apply a force, and the box is going to accelerate in this direction. But it's not the same for all objects. Let's push on this one. We'll apply the same push to it and find that it accelerates less. Why does it accelerate less? You can see in the picture it's a bigger mass. It's a larger amount of mass. And this would make sense if you were pushing on a basketball compared to trying to push a car. When you push on something heavier, it doesn't accelerate as much. And this is building the idea of the equation that relates to Newton's second law, which is this equation here. Our acceleration is equal to our force divided by our mass. So here when we divide by a bigger mass, we get a smaller acceleration. Now in the chapter, I'm often going to write it like this. F is equal to ma, But that first one there, showing how we get that number for acceleration, I think is the best definition of Newton's second law. Just show how it works with some numbers. For those examples when we're pushing on the green box, let's say that the person pushed with 10 newtons and it was a lighter box, it was just 2 kilograms. Well, then the acceleration would be 5 meters per second squared, pretty high acceleration. But if we push with the same amount like we did on the red box, 10 newtons, but now the box is much heavier, 10 kilograms, 10 over 10 is just 1. We're going to get only 1 meter per second squared, a much smaller acceleration. And now we come to the last, the third law of motion, probably the most famous, which is commonly stated as,
for every action, there's an opposite reaction.
And that's pretty much it. I would throw the word force in there. I would say it's for every force, there's an equal and opposite force. But that key equal and opposite is the main part to Newton's third law. So what does that mean? We're going to look at the same example of the person pushing on the green box. But this says when we push on the green box this way, there should be an equal force in the opposite direction pushing the person that way. Now, we didn't see this before in the other example, and if you've ever pushed on a box, you usually don't feel force the other way. But this is if we're getting rid of all other forces, because maybe you have your feet on the ground, there's some friction, and you stay in the same spot. So if it's completely frictionless, or maybe we're floating out in space, it should actually look a little bit like this. The box comes this way, and the person goes back in the opposite direction. Now, I did say equal and opposite force, and in my animation here, we see the person doesn't move as much as the box. Is that accurate? Well, let's see how Newton would approach this. He'd say, let's say we applied 10 newtons to the box. There should be an equal 10, but opposite negative force on the person. So it's looking like it should be equal, but why didn't they move as much? Remember, Newton's second law says that the acceleration is our force divided by our mass. So that negative 10 divided by a significantly heavier person, let's say 70 kilograms in this case, they're only going to accelerate at negative 0.14. Negative because it's the negative direction. But what's the acceleration of the box? Is the same as we calculated before. 10 over 2, 5 meters per second positive this way shows that they appear to move a lot different. So this is an example of Newton's third law, equal and opposite, but how the second law shows how they will accelerate differently. Now, once again, a situation out in space or on a frictionless surface may seem like Newton's third law doesn't apply that much in real life, but it's actually used almost every single time you try and get moving. Let's imagine a swimmer, for example. When they want to move forwards, they're going to grab the water and push it backwards. When they push backwards on the water applies an equal and opposite force, pushes them forwards. Similar for a car. If you want to get a car moving, the tires are going to spin. Based off the direction of the spin, they push the pavement, and in this case the water, backwards. The pavement, which was friction, has an equal and opposite force, pushing the car forwards. Even something as simple as a push-up, where you push your body up. Do you actually push up? No, you push down. You push down on the ground, and the ground applies an equal and opposite force, pushing the person up. So Newton's third law is actually required for pretty much every situation to get moving. And that's it for today's video. I hope that helped you to understand Newton's 3 laws of motion. Thank you so much for watching, and I will see you in the next video.